Okay, welcome everyone to my continuation of what is representation theory. Today's topic is again a random walk, but now more a random walk on a monoid. So random walks on groups is Cayley graphs of groups, which is equivalent to random walks on groups by definition, is kind of an old topic, a classical topic in representation theory and probability theory, whatever you want to call it. But random walks on monoids is relatively recent. So the example I'm using is from roughly 2000. It's called the Tsetlin library. I'm going to explain what it is anyway. It's again kind of a system of a certain random walk type situation, but now related to a monoid. And I'm still very surprised why monoids are not as popular as groups, because in the end, most random walk situations or kind of situations that come up in some version of probability, physics, whatever, should be actually related to monoids and not groups. This is an example. So let's just have a look. It's really this idea of sorting books made easy. So here's the idea. I'm a big fan of the sorting algorithm because it's really lazy. You don't really need to do anything. And I'm pretty sure that at one point I just apply that in my life. Maybe not for books, because I usually only have PDF copies of everything, so I don't have any books anymore. But anyway, you'll still understand the example, even if you don't know what a book is. I hope you know what a book is, but I don't know. If you don't know what a book is, it might be hard to follow. Anyway, so it's a sorting algorithm, and it works as follows. So the story is you need to keep a library organized. Right? That's the idea here. But you actually don't want to do it. Like really lazy, like me. You're just really, really lazy. You have no interest in doing it, actually. So you come up with actually a brilliant idea to organize it using a self-organizing system. And it works as follows. So you have those little books here. And whenever someone returns a book, it just goes to the rightmost spot, right? So the new book always goes to the rightmost spot. And then someone needs to pick a book as well again. So someone then picks this book here, it goes away, and everything just moves to the left. And if this book is returned, it just goes back to the rightmost spot. A very, very easy way of organizing books. Just every new book goes to the rightmost spot. And this is self-organizing. It's pretty cool. So if you run this in practice, it's pretty cool. It's self-organizing because after a lot of time has passed, obviously, just as a stable system in the end, the relative frequency a book is used determines its position for up to a certain probability, of course. Its relative position is determined. So the more popular books will end up more to the right, right? Because they're just often replaced and put to the right. And the less popular books will end to the left. So although this is not really any sorting system, in the end it organizes itself, and you know with a good probability where a book will be. So that's actually not so bad as an organizing system, and I'm pretty sure that this, in some way or the other, is used in real life. Probably not in the library, but I'm certainly lazy, so I'm certainly already a big fan. And I'm pretty sure that my brain likes this as well, in the sense that there are certain organizations I need to do, which I just don't. And some version of this, I'm probably doing it. I don't want to speak for you, but you might do this as well. Who knows? Anyway, so this is a pretty cool way of doing it. And we like to model this and analyze this mathematically, because this is a math channel, I guess. That's why we like to do that, I think. That's my reason of doing it, I guess. And it works as follows. It's related to this idea of Markov chains. And what is a Markov chain? A Markov chain is let's say, a discrete Markov chain. I don't want to go into probability complications. So for me, it's just a graph. And the graph has weighted edges. Here's an example. And the weighting on the edges is such that the sum of the outgoing edges is always 1. Right? There's a probability involved. So you jump with a certain probability to the next, over an edge to the next vertex. So the sum over all should be 1. So sum of outgoings, this one is outgoing, this one is outgoing, should be 1. Perfect. The example isn't messed up. The sum of the outgoing edges should be 1. So this just says with the probability of 30%, I jump. When I'm at E, I jump back to E, or I stay at E, whatever you want. And you just model that in a matrix, and it's called a stochastic matrix, and it's column stochastic in this notation because the column sums, the outgoing edges, sum up to 1, right? So hope I've done my math here correct. I won't guarantee that, but it looks good. So that's just a very simple explanation of what a discrete Markov chain is. So just any graph, right, with any kind of edges everywhere, and just some weighting on the edges to encode the probability. And kind of the idea is now you would like to take some endomorphisms of those graphs, and usually they are monoids and not groups. And that's how the monoids enter. Here's just a discrete Markov chain. Well, and then you want to do a random walk on this Markov chain. So for our library, we can actually model it of a Cayley graph of a certain monoid, of a certain non-group monoid, which is called a band. It's not so hard to explain, and I just explain how the Cayley graph looks like. So in this case, I just have 3 symbols. Let me try to get them in the correct color. So I have a symbol 3, I have a symbol 2, and I have a symbol 1. And my action of the 3 edges, so I have a 1 edge, I have a 2 edge, I have a 3 edge, as you can see, is really just, well, let's have a look at this expression here. So if I add act with 2 on this, act with 2, it's not quite, so we already have the book. Anyway, so it's really just the book reorganizing. So 2 goes to the right, and so you jump to the next expression, and the different expressions here just are the different orderings of those symbols, right? There are 6 orderings, so I have 6 vertices. So 2 acts by jumping to this place, 1 acts by jumping to this place. Doesn't make sense. I add 1 to the right. It's really just adding to the right graph if you want. And 3, well, 3 doesn't do anything. So that's a Cayley graph of a certain monoid called a certain type of band monoid. Has a name. Very easy to explain the action on this Cayley graph. It's just exactly the library that we had before. And now we can think about a random walk on this graph, and you should be able to apply the same techniques from the group case, and you should get some nice statements in terms of characters of the monoid will determine as the eigenvalues and then the long-term behavior of the system. In this specific example, it takes the following form. So the eigenvalues of the Tsetlin library random walk, which is really just a random walk on this graph, and now you would weight the edges by the probability. So you could actually do that like the frequency a book is used in this example. You could weight everything equally or whatever, but it should be a probability in this sense. So sum of outgoing edges should be 1. That's just it. And you can then write down the eigenvalues in terms of well, of a function, which in the end, we'll explain that on the next slide a little bit at least, is just given by certain characters of the group. And you can write down explicit formulas for all of these, and I've done this here. So in my example that I used here down below, the book 1 is not very popular. The book 2 is reasonably popular, and the book 3 is then also, well, mildly popular. And you can write down the matrix. You should have, I hope I haven't messed up, you should have 1 as a column sums in each matrix. You can write down the eigenvalues. You could count the number of eigenvalues as the number of fixed point free permutations of a certain set. So fixed point free permutations of a set of size 0, 1, or 3, right? So it depends a bit. So S number of books is 3, and if X is 3, then this is S0, and of course there's just 1 fixed point free permutation, and it's the eigenvalue given by just the probability. And if X is 1, then this is S2. So how many fixed point free permutations are there in S2? So these are the permutations in S2, and obviously only this one is 6.3. So there's only 1. So each one appears just once. And here's S3. How many fixed point free permutations are there in S3? Let me try to draw them. Here's 1, and here's 1. So actually 2. Anyway, so we can count the number of eigenvalues and also their forms by just, or the precise values, by just using a very combinatorial approach, like counting number of fixed point free permutations and summing over the corresponding probabilities, not eigenvalues, probabilities. And you get the corresponding matrices. So it's pretty good. It's pretty cool. This is how it works in this example. And well, I haven't really explained it because I haven't really explained what a band is, but this is really related to this representation theory of the associated monoid, which is this band monoid, which takes roughly the form here. So this is a cell picture of the band. It's a really strange monoid. Everything is an idempotent. So you just have this funny cell picture here. So here's 1, 2, 3, and then you have more expressions and more expressions. And you can prove what I just said is true, this pattern here. This is just the answer, right? You might think of how to prove it. You actually do it, and it's linked in the description. It's very nice, quite nice paper linked in the description. You could phrase everything using the representation theory of a certain type of band monoid of this form, which I don't want to recall. That's why I'm a little bit hand-wavy here. And the library itself is then just a special case of random walks on monoids. And the result I showed you, the counting result, which in the end will then determine the long-term behavior by taking powers, and you have eigenvectors and eigenvalues and so on of the system. It's just a special case of random walks on monoids. Or semigroups even in general. They don't need to have identities. So this monoid actually doesn't have an identity. How can you see that? Well, there's no unique bottom cell. That's kind of missing here. It has 3 bottom cells. So this is a semigroup and non-monoid semigroup. Difference doesn't matter actually. Okay, I was a bit hand-wavy. I'm always hand-wavy, but in this video I was a bit hand-wavy because I hadn't explained what the underlying monoid is. But I hope you still got the point. There is a monoid, and you can model this library, the long-term behavior, the eigenvalues, whatever, as a random walk on the Cayley graph for that monoid. And then you get the usual results, like eigenvalues are determined by certain forms of characters and so on. And you can solve that explicitly, and you get the explicit solution I showed you by just counting fixed point free permutations, which is a pretty cool idea. And yeah, this is just one example of a random walk of a real-world example. Is that a real-world example? I'm not sure. I say it again. Probably this organizing system is applied very often. But anyway, let's call it a real-world example, which doesn't come from a group, but it's really related to a monoid. And there are quite a few of those examples. And this is a relatively new field, and not too many examples are actually studied in the literature of random walks on monoids. But it's very, very similar in flavor. As you would imagine, hopefully by now, you can expect, or you would expect, that it will be group theory plus cell theory. That's exactly what it will be in the end. It's pretty cool. So if you want to have a look at the paper linked in the description, it's relatively readable. And it's also some Sage code linked in the description, which you can run yourself, which runs this example for you and computes a very general version of the eigenvalues and the eigenvectors. Anyway, I hope you enjoyed the video, and I also hope to see you next time.